Does it work? Okay, let's see. So last time what we said is that so we were calculating the spectrogram, taking a time series, looking at power spectrum over multiple time windows, and from this we had this classical representation which shows the peak here in red, and we say that this is the basis of the spectral analysis that can be done, and then it's done automatically. You have to just in Python or in MATLAB, there's a spectrogram command that you want to make sure that you are using it correctly. The difficulty is to find the size of the window with respect to the features in the signal. So if you have a window which is much smaller than a spindle, it doesn't work. You will not get great stuff. You need to make sure that the motif in the signal is such that you have several of them in the window. And then you can have a sliding window with an overlap of 90%, which gives you a smooth representation. That's important. And it's not only true for EEG, it's true for many motifs. You need to have several of them in the window in order to extract what you want. Okay, we discussed the spectral decomposition. We can have general anesthesia, sleep, or this Stein-Rubenbeck representation. We discussed last time the fact that the power spectrum, the spectrogram, give you here information about the statistics of the amplitude of a given frequency. That's why you have something in red, which is consistent, which is coherent, and give you the peak. And so a way to segment is to use the region where you have this high density to detect. Usually we do detection directly on the signal itself. Okay, so that's what you can achieve having the spectrogram, having a sliding window. You can detect where are your motif of interest. Here this is the spindle, and where it is located, and how this mean frequency evolve with time, because we said at the beginning of the class that there might be no information if the motif itself. There is information in their statistics, but to get information about the statistics you have to extract them one by one and get a correct segmentation. Okay, and finally I explained last week that if you have a signal, you can get from the Hilbert transform, which in the Fourier is just you multiply your signal that you have original signal, the Fourier of the signal, by the sign here. It's just a pi over 2 changes with a minus, and this is a way to form the envelope, because when you have a signal plus I, y, you can write it in the complex plan as the radius and the phase, and the derivative of the phase give you the instantaneous oscillation. This is how you define oscillation at one point. Right, you remember, if you want to define at this particular point what is this oscillation, it's not easy. It's not easy. So you need to go through all this process, which means calculating the Hilbert transform or the Fourier transform on a given window, and all this process, ultimately the accuracy of your instantaneous omega depends on all this procedure. And this is how you can define instantaneous frequency. Okay, so now I want to start with how to track a rhythm across a signal. That is, suppose you have a rhythm. How can you track this specific rhythm? What do you need? You take your signal, x of t, you can decompose it in a sliding window, and you can do the Fourier square. You have your Fourier transform, you can calculate the power spectrum. And interestingly, your power spectrum can be decomposed. I don't know if I have one here. So let's go back to this power spectrum to have everything clear. I would like to decompose for each window the signal according to what you see in this power spectrum. In other words, I would like to say this is composed of a peak plus a decaying behavior. And so if I do that for each window, I'm asking, for example, is the peak or the size here changing in time. In other words, I would like to fit this, and if I am able to fit this, I would like to remove this from the rest so that I get, in the end, something that will look like this. And then I will say the signal is decomposed by a decaying component, which is called 1 over f component, plus an oscillatory component, which is oscillating, let's say, at 12 Hertz. So I have this 12 Hertz component, and so I can say the signal is the sum of a 1 over f component plus an oscillatory component that I can capture. And so I want to do that at each moment of time to extract the parameter of this decomposition. That's the goal of tracking a band in time. So how am I doing this? Where is the eraser? I think it's over there, no? Okay, is that clear? That's what we want to do. Okay, so let's continue. So, you have a sliding window. On this sliding window, I will approximate the 1 over f component using a function that depends on time t. This is time t, t plus delta t. You have your sliding window. You calculate the power spectrum, and you get something like this. It will have something of this shape. So what we are saying is that I would like to capture this using this component. That is, at a fixed time, it's a coefficient a divided by b plus f to some power p. I want to calculate this power p. For example, you can say, well, if I neglect this b, I have something like 1 over a to this power p. I take the log of this, and then I fit a curve, and I will get a minus p log of f. So as a function of log of f, it's a linear function that you fit. And you get p as a regression. And you can say, well, you have to be careful, so you can take a segment where you get it, not necessarily up to 0, because if it goes to infinity, you get some deviation. Because it goes to infinity when f equals 0. So you have some deviation, so you give a little space for you to fit, then you get your p, you get the coefficient, and then you can go back and add the c, because when f goes to 0, it goes to a number, and this number you can grab from the interpolation here. Alright, so this is how you get this component. Fine, you get this component, and then the next thing to do is to say, in addition to this, the power spectrum will be the sum of this component plus this oscillatory, and one way to do it, this is not what I showed you last time using the Holstein-Uhlenbeck process, but you can say, why don't I fit a Gaussian? That is, if you remove this to this, so I take this general feature and I remove the dashed line, what do you get? So if I take EEG, or spectral P of EEG, minus this 1 over f component, which is equal to this, what do you get? You get a signal that will look like this. And so one possibility is to say that I'm going to approximate this using a Gaussian. So fine, how do you do the Gaussian? You take your fk, the center of the Gaussian, let's call it f1. This would be f1, and you extract the information about the variance, which is sigma, that you have to fit. And that would give you and if you have many bumps or many peaks, you can repeat this because the Gaussian converge very quickly to 0. You can have this as a decomposition of independent Gaussian. And that's a way to have your decomposition of the signal. This is called F-foof decomposition. And the way to do it is it's called Irada methods. Irada method, this is the method that has been developed to extract this 1 over f components. Usually they do it a bit differently. They subsample at different delta t. so that will get rid of this bump. And then they do basically the fitting. So we saw last time that it might be it's not derived from any model. So maybe this fit is purely arbitrary. The fit, and the correct fit to do is what we have shown you using this Orstein-Uhlenbeck process. You have to fit a different function. But I don't care about this, because this is not what you care about, having a true model. You care about having this decomposition that will give you the parameter A, P, CT, this frequency, the width here as a function of time. And you want to see this over your signal. That's what you want. All right. So when this is down, you can move on. You move on with your, you have this parameter, 3 parameters for this 1 over f component, and 3 other parameters for the oscillatory component. And this is what we published last year, last January, in this neuroimage paper. All right, so I explained on the left this decomposition. This is what we just discussed now, and I'm going to show you the result on a full EEG signal. That's your EEG signal. You take the power spectrum of your signal and you see the component here. Well, you have your 1 over f here component that you extracted here. Once you extracted your 1 over f component, you can subtract this 1 over f and get information about the oscillatory component that you fit, as I explained to you. So here we had 2 components, one for the alpha, or the theta, and one for the delta. So you have this component, which is not that nice, because if you subtract it, it's not beautifully, the signal doesn't necessarily lie on one side. That's on one side of your approximation. That's why here you have a peak that is negative. But anyway, you can transform this, and so you have this oscillation, so you have to approximate this by a first Gaussian and this by a second Gaussian. You have to make sure that what happens if the 2 peaks are not too close together, that you will not have one Gaussian that will fit both of them. Alright, so this is the implementation of this procedure, this algorithm. Signal, TSD, you have the 1 over f, you remove the 1 over f, and you get this 2 Gaussian to fit this. Okay, let's ignore this point here. Alright, so this is just to repeat the procedure. You go in the log scale, you fit 1 over p to this power 1 over p in the green, and then you have to fit to add the c, because it doesn't go here to infinity, so you have to correct. And once you remove this component, you see sometimes there are things that are a little bit below, then you subtract, and you have the first peak in here and the second peak here, and then you can approximate. Alright, so that's a procedure which is somehow robust, and you can apply it. And what we did is we applied on the EEG signal to ask, are there information in the coefficient we extracted? I show you we extracted several coefficients, one for the 1 over f and the other for the oscillatory component. You have the EEG, time 0, no concentration, the mice is awake. This is when you start the concentration of anesthesia, and then when you stop. That's the spectrogram associated to this. So you see a general trend that when you start the anesthesia, you see that the between alpha and theta power goes down. This was captured by this curve, and so how do you create this curve? This curve is simply the Gaussian that you fitted at each moment of time with a variance. So I don't remember if it's sigma or sigma divided by 2. So this is the Gaussian. The Gaussian is at the center here. And you can estimate, you can plot the variance of the Gaussian plus sigma divided by 2, the mean, the center of the Gaussian, so which give you this uncertainty. And you see that it decays. Great. So that's the plotting the oscillatory component which allows it sometimes to track the bands. You can see here the bands, the alpha bands or the theta bands, and then here the more like the delta bands. And okay, the problem is, of course, when suddenly you have no signal, you have nothing to fit. So the coefficients will be 0. So sometimes you have an interruption. Then you can ask what we wanted to do at that time to say, but under some condition, this is something that would be interesting to do, is maybe we can have a curve that will interpolate, the same as you have a spline that will interpolate between this point and that point, to say that although the signal was not strong enough, we believe that what we should see is something like this, if it's necessary to do it. So this is for the oscillatory component. So it shows a certain behavior, that if I show you this, the signal itself, it's very hard. You have to go through this decomposition. And then we have this P of t, so the power here. And so the question we ask, how this power was changing according to the different moment of anesthesia. And so you see here how this power is, how this power here is changing. This is this purple curve. So it seems that you have something between less than 1, and when you go into this direction, you go for a P that is closer to 2 and at least above that what you had there before. So it gives you some information. Okay, so yeah, so then what we wanted is to compare. For example, now you can say I have a way to disentangle these different powers, so you can look at how the power delta and the power theta evolve as a function of time, and try to correlate. So the power delta is you take your signal, you filter it in a certain bandwidth, which corresponds to data, and you calculate the power associated to this as a function of time. That's those curves here. And what you are interested in is this power correlated to the coefficient P of t that I just showed to you. So for this you have to plot the two, and you can just see by eye. You can see the correlation here between this signal and the delta signal. So this gives you some relation between the parameters that are not obvious. And then you can look not only at P, but what happened for the other coefficients, A and C, which are a coefficient of the non-oscillatory component. And with this allows you to calculate some correlation. I'm not going to enter into the detail of the correlation, but this is just to show you that you can follow in time parameter that you estimate that you think can contain or not, because you don't know at this point if they are going to be exactly following the power or not. So you have to try. Okay, so I'm going to stop here for the last part about pushing as far as we can the Fourier analysis with the power decomposition. Now I would like to move on with a very crash course about wavelets, because this is impossible for me to cover this. And but I need this because we based one of an important algorithm on wavelets to remove artifacts. And I just want to explain how this is done so that it can give you ideas of the process. So wavelet decomposition is like Fourier transform, Fourier decomposition, except that instead of doing on sine and cosine, you have to you do it on there are special classes of function. Let's say here we have a function that is exponentially decaying with some oscillation. So this is an example of what is called the Morley function, psi. So you take any function x of t, and you would like to decompose it on this power, on this wavelets. The importance of wavelets is to be focused in time. It's not, the signal doesn't have to be periodic, And if the signal looks like this function, it will give you the maximum coefficient, which means it accounts for local oscillations. And when you multiply here by A, it accounts for scaling. That is something that could be the same, but at much more smaller scale. And the beauty of the wavelet approach, which has been known for the last 30 years now, is that when you calculate, so this equivalent of the Fourier coefficient, from this coefficient, you can recover the function x of t, which is called the synthesis. That is, if you have this, you can integrate over b and a, and you recover the function, which means that you can use this as we do in Fourier series. In Fourier series, if you truncate, you have, let's say, 100 terms, you cut, and you want to approximate your function by this, you can do the same here. What is interesting, and when you do this, it's equivalent to have a bank of filter, which I will explain a little bit, that, for example, look at the function and approximate it according to, let's say I want the frequency between 0 and 2, between 2 and 4, between 4 and 8, between 8 and 16. So it's a way to approximate function by keeping components with, let's say, a given range of frequency, which is interesting. So this is a wavelet coefficient. You can reconstruct and you can calculate the power, the equivalent of the power spectrum. Yeah, maybe this formula is a bit complicated, but maybe you can grab some information about the coefficient and you see at which frequency this is important, and you can get this by some derivative of time. Okay, let me not go into this. It's too complicated for nothing. The main message is that from the coefficient, you can reconstruct the function. Great. So this is an example of an EEG signal. You can have a filter signal between 8 to 12 Hertz. And you can have here what the spectrogram will give you on this. It's not very well resolved in time, but if you do the wavelet transform with the Wilson wavelets, you get something quite resolved. Although you have here this very elongated component here, you see this very resolved component at 10 Hertz, which here you don't see. You see this very blurred representation. So you win here time and space in the resolution, and that's why this is interesting. So associated to this, you can see this event here of spindle type events, right? And this also allows you to segment them in a very nice way, not like this, where you see that in commercial devices, where you don't get the time resolution. Okay, so this is to show that wavelets can be used to gain into accuracy.
So does that mean that the wavelet transform gives you information about the shape of the signal? Because with just a Fourier, you don't really know the shape, right? I mean,
what do you mean by shape?
So, for example, in this case, if you have red spots on the CWT, right, on the wavelet spectrogram,
yeah,
it means that part of the signal, it looks like the Wilson wavelet with.
That's right. It looks so at this resolution, which is interesting.
Okay. So
because but in principle, you convert this into a spectrogram, which means that I have a very good resolution here in terms of frequency, because I have a motif that is very well respected. That's why you have a high the red here. It's high intensity for this. So you get with this the information about local shape, much more accurate than if you had a sliding window. So this what we used some time ago, where you had suppression, the burst suppression, the motif which is very clear. You see, and so you can see what you have in here. And now if you do the scaleogram of this, what was interesting is that, so you do the scaleogram, now you can use the fact that you have different band decomposition, as I said to you, from 4 to 8, 8 to 14, whatever, 14. So you have these different bands, and you can see in these different bands, in this motif here, what are the predominant signal? What are the predominant power of the signal? And this is very nice, because this allows you to see, which is very hard to see like this, a very specific segmentation that you can use to quantify this burst. Okay, so So you take your wavelets according to Morley. From this, you can get your scaleogram of your filter signal. So this is the way to filter. You get here this signal, that signal, and this signal, and from this you can calculate your scaleogram, which will give you the information and allows to have a specific segmentation of the moment where you have, for example, a dominant of the alpha band, a dominant of the beta band, or dominant of the theta band. And so that's what we said at that time. Hey, maybe this is interesting. We have identified two motifs here, one motif there and one motif there, and then you can use this to go on into the characterization of a burst, of something that has not necessarily a clear meaning in this way. It's not clear how it is decomposed of. And by doing this, you can assign a sort of dominant frequency band according to where you are. For example, you have this theta band that is dominant toward the end. The beta band seems to have two components, at the beginning and in the middle. And then you can look at the difference between this difference in time between the motifs. Okay, so that's the same to just show you on the scaleogram how do you have very nice resolved positioning of these fast events. Okay, so right now up to now I discussed the continuous Fourier wavelet transform. What has been done is that you can quantify the wavelet decomposition according to some d-adic band, for example, from 1 to 2, 2 to 4, 4 to 8, and so on. So you have different bands, and you can do that in a discrete manner. You don't have to calculate the integral, but you can use a discretization that allows to separate. So for example, you start with your band here, and it will separate this into two. One, the low component, 1, 2, and then the rest, the high component. And then what you can do is you can really iterate this. That is, you separate your filtering, basically. This is low, high, and then you repeat. Then it will become, you can divide into two, and this will become low again and high again. This will give you what is called the detailed and the approximated coefficient, and you can reiterate this process as I just showed you here, and you have a certain level of decomposition, one, first line, and then the second level of decomposition, you have the first one, and then you have another one, two, and so on, and you can move on this way. So you have different levels. So this would be level 1, level 2, and then you redecompose, and you'll have some accurate, more you get here, and more you get refined coefficient, more it's going to be refined in frequency, and more you go in that direction, more it's going to be low frequency type. So this, what people have used to say that finally we can decompose any function which is L2 integrable, that is, could be very complicated, into different subspaces which account for the different frequency. And so the way to do it, you need to have two conditions. I mean, this 2 to power j is a way to magnify where you are, and this is the translation in time is to say where you are going to be in your sliding window. And when you combine this, you take your wavelets, you multiply by this coefficient, and you can translate it. And so this is for what is called the scaling function, the wavelets function, you do the same. You take the scalar product the same way that you do it in the case of Fourier, but instead of having ck sine whatever omega k t, you get your scaling, which is given by this, which is a function psi that has to satisfy some condition. And then you do this at a given scale. That is, if you are between, let's say, you're interested between 16 Hertz and 32 Hertz, this is a way to filter you filter by having the right component here, and you decompose on this function. So it's equivalent to have a function, you filter it in a band of frequency, and then you do some analysis, and then you do your decomposition at this frequency level. All right, so that's how it works. And then you can add the subtlety, is that if you want to be more refined, I say, all right, what happened if you go to between 32 and the rest? You have to calculate this at j plus 1. And if you sum what happened at j plus 1 with what happened at this component, you get more of the function. And in the end, when you want to get everything with starting from 0 to 1, from 1 to 2, and so on, if I want to have all the detail of the function, I need to integrate into sum of all this frequency band. That's what it says here. You have this projection, Pj. It's a bit of mathematics, but you have to understand where it comes from. Pj is mean the projection on this frequency type. And then the projection of all of this, which is in there. And then in this, at this scale, you have this function, which is the decomposition. And when you want to sum everything, you have to take the sum of all the components. Yeah, so that's what I'm just saying here. It's the mathematical definition of you have all the details. You sum all the space that you're interested in, and the rest is your approximation. And in the end, if you do that at infinity, this means that your function f should be the sum of all the projection in all of this space. Why I spend just 2 minutes on this is I want to discuss the application. Now it becomes relevant in terms of why we need to do all of this. Suppose you have an original signal. Suppose the blue is the original signal. And you get a perturbation because the eyes was moving or whatever. This is example of artifact motion. Something has moved and it created this. But in reality, I want to recover the blue. How am I doing this? How do I know how to recover the blue if I got something like this, which has perturbed everything? So this is an example. This is when you blink, eyes are blinking. Instead of having the correct signal, you have this, and I want to correct it. And the question is, I will explain to you how you get the blue. The blue is a correction. And this is an example of electromyogram, this muscle effect. You have this oscillation, and still you would like to correct it. Why you want to correct? Because in real time, this create discontinuity. And you don't want to calculate any of the coefficient, anything that's of interest, and accounting for this, because it has nothing to do with reality. So how do you get rid of this? Okay, so for this, you can say, I'm going to decompose the signal using the wavelength decomposition the way I explained to you. That is, there is the refinement of what happened at different frequency, and there is the rest. And if you think that the details of the information of all of this is contained in the coefficient, you can calculate for each specific frequency band, this M here, for each band, 0 to 1, 1 to 2, 2 to 4, for each of these bands, I'm going to look at the distribution of the coefficients that you have. So you look at the distribution of this coefficient. And this is a 3 example I showed to you, and this is the results. The EEG at different levels, for these different bands, there is a certain distribution of coefficients. But if you look specifically at the EMG signal or the EOG signal, or the eye signal, you see that the distribution is very different. So you are interested in the difference between this distribution to say, look, if this is a standard EEG, if this is a standard distribution, I probably be able to use this in real time, because that's a difficulty, to remove this signal and in some sense to project or to recover the correct signal from this. And the question is, how do you do it? So this is fitted by some Gaussian here. I think sigma, yes, sigma is incorrect. I think it's beta that we put it here. So you have not necessarily a Gaussian all the way. You can see here there's some kind of asymmetry. It's very sharp. And you capture this sharpness by beta. If it's 2, it's the Gaussian. But if it's not 2, it's very peaked. The beta is going to change. So this is a way to capture this information, right? Beta is sigma. Okay. So what we patented a couple of years ago is the following. You have a signal which is okay. Signal is okay. And suddenly you have something with an artifact. So you need to have a way to detect artifact, which I'm not going to discuss. But suppose you know where is the artifact. Then you can use your wavelets coefficient at different levels. So this is a very, it's like filtering. You filter at a very high frequency and then you go lower and lower. And you would like to compare this with the reference, because the reference is your proper signal. Everything that is deviant from this, you would like to subtract. So that's what we did here, for example. You see that in some sense here you have some kind of a baseline. And you want to say that to recover or to remove this low component, one way is to transport the coefficient or put this coefficient here to the level of the coefficient we have before. So you take this piece, you transport it here, and instead of having this coefficient, I'm going to take the transportation and replace this coefficient by the coefficient that has been transported here using the reference. And that's what you can do at each scale. And that's what turned out to be robust and can be used in real time without having a predefinition of an artifact. Because what people did in the last 20, 30 years, they say, I have an artifact. I'm going to use independent component analysis, which means I have a pattern to recognize, and I'm going to see if I see this pattern. But this pattern cannot necessarily be the same all the time. So the large variability of this pattern, that's why most of this approach failed. Because if you have an oscillation like this, which is your artifact, or your artifact is a little bit bigger or smaller than what you see here. You see, suppose your artifact is like this, or like this. If I give this, and your machine learning to learn, I will not get this one. But the next time I get this one, it will fail. This has no such representation. We use the statistics. And by using the statistics, by comparing the statistic before and after, we say the statistic should not jump. There should not be a jump. If there is a jump, it means it comes from somewhere else. The brain does not jump in terms of power, different frequency. That's what our assumption.
So you're saying that the benefits, the strong points of this particular algorithm is because it's agnostic to the shape, right?
That's right.
Now,
that's right.
My question now is, the reasoning for using wavelet decomposition is because you want to match a shape.
I don't want to match any shape.
So how do you choose the mother wavelet?
The mother wavelets, we will see, doesn't matter. Okay. Yeah. I saved the slide. Okay. I saved that one. I didn't know that I will have the question. Okay. So you calculate from this the empirical cumulative density function. So you look at all the coefficients that are less than something, and as a function of x, when you exhaust everything, this will go from 0 to 1. So I take all the coefficients I have, and I look at the cumulative of those coefficients. So this is the cumulative of the artifact, and this is the cumulative of the good signal. So how do you perform your transformation? You look at the coefficient in here, which if the distribution didn't change much, they should align like this, like what you see here. This is a different level. But for this level, they do not match. So you take a transformation that will take your coefficient and propagate it here to the artifact, and then you take back from this transformation, you go back to what is the reference signal, and then you grab the new coefficient that you should use. And this is a transformation. This allowed to transport, to use this difference in the cumulative to do this at a given scale. And finally, this is the algorithm that we developed. Take a signal, identify the artifact, decompose in wavelets at different frequency, very high frequency, very low frequency. At a given scale, do this transportation of the coefficient, and here I'm not going to discuss, there is a normalization. So you transport the coefficients that are deviant to the one of the distribution, so that if they are too large, if they are too small, if the coefficients are below, you don't do anything. That's why we have a normalization. But if you are above what should be the normal signal, it means that this is an artifact. And so we transport this into this one, to the one that was obtained from the reference. Once this is done, you go back to the signal, the clean signal, and you can sum them, because as I said at the beginning, you can sum all of this and it gives you back the signal, and then you have a clean signal from this. Okay, so this is examples. You have a reference signal in black, you add an artifact, and in blue you get your cleaning, and you are interested in how good is the black with respect to the blue. So the artifact is added. You have an artifact, you add it on the scale, so you know the truth. Now you can compare, and so you can compare in the case of ocular signal versus the myogram. You see, myogram is much higher in frequency, the type of artifact that you have. So you see that they're going to perform nicely. You can recover the black with respect to, recover from the blue, it's close to the black. And when you look at it specifically, you say, well, where at which scale there was this deviation? The deviation was here, of course, at low frequency. At high frequency, the two signal matches, the cumulative are the same. But at low frequency, no, and this is where you do the matching. And the rest, you don't touch much. This is because of this low frequency. But here, because it's at high frequency, instead of doing this at low frequency, as we did here, it does this at higher frequency, because this is where you see the deviation. And that this is very nice, because this is universal. I can do this if I have high frequency artifact, or if I have a low frequency artifact. It accounts for this diversity, because I can do all of this at each scale, at each frequency scale. You can use this even in image processing. This is in 1D, but you can also do it in 2D. Right? Now this is Jim's question. So you can try on different types of wavelets, which is called Debussys. And again, I would have need another hours to explain, but there are different types of function you can choose. You see, you can differentiate the Gaussian, which is called the Mexican hat, and there are people that have constructed wavelets, also looking at their Fourier transform. And when you do this, what we found out that it doesn't matter which wavelets you are using. It's robust, because the principle is to transport coefficients. Of course, the wavelet, they have to satisfy, some conditions. It has to be called wavelets, so that they have, there are some criteria. Okay, I want to stop here for this part, and we're done with signal processing. I think with what I explained to you, you can start looking at Wikipedia, at Google, at the book on wavelets, the book on Fourier transform applied to signal processing. I think you're ready for this type of investigation. So now I want to stop this and to move on with neuronal networks. So if you want, we can make a break of a few minutes, and then we start with 20. Let's say I do half an hour.